All right. Our agenda for today or this evening is the geoelectrical methods. And the scope of this lecture is just about the simple direct current resistivity method, right? I understand there are other electrical methods like the induced polarization, right? However, for this session, we'll be just focusing on this one method. Particularly, it's the most versatile electrical method, and it's relatively cheap to build, right? And let's talk about the theory. Um, the important premise here is that rocks and materials are electric do have electrical charge, right? They are generally neutral. However, if once you introduce an imbalance, like a physical or chemical process, you can actually induce the flow of you can basically trigger the base materials, okay, and read themselves in terms of an electrical charge. Okay? And the other electrical methods like self-potential and induced polarization are actually based on this principle. However, DC resistivity, or our main focus for this evening, is simply based on the flow of current, okay, rather than the potentials. Electric current is always about the flow of charged particles. It could be either electrons or ions, right? And the direction of flow is always from the positive to the negative. And electrical current is measured, or it's also abbreviated by the letter I, and is measured in the units of amperes, right? And amperes refers to the amount of electrical particles that's passing a point per second. Okay, so amperes is the rate of generally how many electrically charged particles are passing per second. And current is simply a result of potential difference, right? A current will flow whenever you create an imbalance in the electric potentials, right? And for most materials, you get actually an you actually get more current whenever you have an increase in the potential difference, right? It's just similar to your potential energy and kinetic energy. Like the higher you fall from a building, the greater your velocity, right? So the more current you have, the bigger the potential difference, the bigger the electric current. Right? And the relationship between potential difference and current will depend on the material, right? So we have established that the more potential difference you have, the more current you get. And that relationship will also be dictated by the material or the media, right? Where when I say media, I'm talking about the general collection of materials, right? A material just refers to just one substance. When you're talking about media, it could be like a collection of rocks and soils whatsoever, right? And the relationship between the potential difference in current is proportional to what we call the resistance of the media right? And it's called the Ohm's law. And resistance is measured, right, in term using the units of ohms. And in turn, resistance depends on the electrical property and size of material, right? Resistance is different from resistivity. Resistance simply refers to the bulk media, right? The more material you have, or the longer the material, the bigger the material, the greater resistance you get. And and conversely, the thicker the material, the thicker the media, or the wider the media, the more electrons could pass through it, right? So you're actually getting a decrease in resistance when your material is generally wider with respect to the flow of the electrons. You can compare this, or the good analogy here is a highway. The bigger the highway or the more lanes you have in your highway, the more vehicles you could pass, the less traffic jam. Okay. And similarly, for resistance, the bigger the cross section or the wider the path, the less resistance you have. And therefore, we can describe resistance in terms of the length and the intrinsic property of the material, the resistivity, and also the cross-sectional area of the material, right? And this equation is just a rearranged form, okay? Generally, resistance is just equal to resistivity multiplied by the length and divided by the cross-sectional area, okay? But this in this equation, we have it rearranged to show how we can calculate resistivity because this is the main unknown when we are doing DC resistivity survey. Right now, resistivity is, or the raw is measured in terms of ohm meters, right? Okay. Right. Another principle here is that apparent resistivity is the overall resistivity of multiple layers, right? I think we have discussed or we have briefly tackled this in the previous lecture. The stacking velocity, right? If you remember the stacking velocity, or yeah, or at least better analogy is the two-way travel time. The two-way travel time, for example, is always about the time you spend traveling through the layer plus all the overlying layers, right? And that's the same with resistivity. Whenever you have multiple layers in the subsurface, like for example, beds, strata, or soil, and then bedrock, as long as you have multiple layers of media, the resistivity that you're gonna be measuring is what we call the apparent resistivity. And this will always be an average, right? It's sort of a weighted average of the resistivities of our materials. And we have another relationship here, the conductivity and resistivity. Conductivity is simply the inverse of resistivity, and conductivity is measured in terms of Siemens per meter. Although we're gonna tackle this topic probably in the other lectures because conductivity is used for electromagnetic methods, right? So in essence, electromagnetic methods just simply measure also the electrical properties of materials. But again, we're gonna discuss that later in this term. Sorry. Uh, mhm. Right, let's talk about the resistivities of different materials. Most minerals are actually insulators, like they don't really conduct electricity. However, I mean, like for example, if you have a pure diorite or maybe pure gabbro, right, or maybe pure andesite, chances are those rocks are actually mostly composed of insulators. Okay? Right? However, rocks will definitely have pores. They will also have joints. And whenever these pores or joints or cracks are filled with water or conductive materials like ore veins or conductive soils like clays or other minerals, right? You get to introduce or you get to actually lessen the resistivity of your materials. Okay? Pure water is technically a good insulator. However, you will rarely encounter pure water unless you have like a good quality distilled water, which you can only produce in a laboratory. And therefore, in the nature, you will always encounter a impure water, which will contain salts, particularly ions from weathered rocks. Salt water, right, also has ions, which also conducts electricity. Particularly ions can just move through your water, right? And it can induce an electric current. And this is actually an important way of transmitting electrical particles. Like ions are technically different from like ionic conduction is different from electronic conduction in the metals, right? Because in the metals, the only thing that's moving are the electrons, whereas in ionic conduction, the ions are the ones that are moving. And for geology or geologists, we are mostly interested in ionic conduction because this is the uh, main method in which electrically charged particles move through your rocks and soil. And this is another important premise in resistivity. Rocks and soils are very sensitive to water content, right? When you're doing a resistivity survey, this is the first thing that you have to consider. Where is the water table? And what are the conditions of what are the moisture conditions of your soils and rocks in the subsurface, right? A dry soil versus a wet soil will have drastically different resistivity values. Okay. Right? Concentration of salts in water are usually low. However, of course, if you have your site, for example, is just near the sea, you can get some leakage like through saltwater intrusion. Okay, and that can increase your conductivity and subsequently decrease your resistivity. Right? And again, I'm gonna hammer again this statement. Resistivities are very sensitive to water content. And the implication of that is that the range of resistivities of rocks and soils are actually very large because of this factor. And it makes it almost impossible to actually determine the rock type just based on the measured resistivity values. This is the biggest pitfall when you're using resistivity. Actually, any geophysical method, all geophysical methods in general will have a very large range of measured physical properties. And most of the time, it's impossible to determine the rock or or soil type solely on the measured physical property. That's why it's also important to properly construct a geologic model. To be specific, it could be something like a simple stratigraphic column for your site. Just describe what you think is the soil, what soil type do you have, what is the rock type, what are their probable depths. Okay? And you can determine that, or at least you can construct a rough local stratigraphic column from, of course, from doing some field work, studying the geomorphology of the site, looking for outcrops. If there are available old drilling logs, that would be good. Okay, so on and so forth. Or alternatively, or at least you can also do another geophysical method, right? This is not really an uncommon practice. Sometimes we combine two different geophysical methods in order to constrain the rocks or soil types, right? But local stratigraphy is always very important in geophysics. It's usually the easiest way to constrain your interpretation. Sorry. Right, for example, let's talk about granite. A granite rock with 0% water will have a resistivity of 10 raised to 10 meters. Once you introduce like just 0.19% water, it will decrease by 10,000 fold, right? Sorry. Yeah, that's correct. Okay, it will decrease by a factor of 10,000. If you if you increase the water content to 0.31, the resistivity will decrease again by a factor of almost 1,000, right? Right. Therefore, again, I'm gonna hammer this statement for the third time. Resistivities of rocks and soils are very sensitive to water content, right? This is the first resistivity will always show the boundaries of your moisture conditions. That's the first thing you will see in your resistivity survey. Okay. If you want to interpret something more than that, like interpret the rock type or soil type, you will need to construct your geologic model for your site. Right? Again, we have our special material clays. Clays are like aliens in the world of geophysics and engineering. They have so many special properties. Okay? Clays microscopically are like plates, right? They have plate-like structures. Okay, and some of them have like open structures which can trap water. Some of them have sandwich-like structures which can trap water in between those plates, right? And this property allows clays to be actually slightly electrically charged, okay? And again, they also have a large surface area per volume because again, you have Clay minerals are have a plate-like shape, and yeah, that allows them to trap water and generally makes clays generally conductive, or they generally have a low resistivity, except when they are dry, right? So again, I'm gonna hammer again for the fourth time. The moisture condition will greatly affect the resistivity for materials. If clays are dry, they're generally resistive. However, when they are moist, they become conductive. And within the soils or even rocks, like soils, clay soils or rocks which contain clays, like your mudstone, shale, mud rock, weathered, all forms of weathered rock will mostly contain clays. And these soils, rocks which have clays will generally have lower resistivities. Okay, right? Clay soils, for example, will have resistivities in the range of 1 to 100 ohm meters. Okay, or generally within 10 to 100 ohm meters. And we also have to distinguish between your clay minerals and your physical clays, right? What clay minerals, when I say clay minerals, we're technically talking about the kaolin, illite. I'm sure you're familiar with this with your mineralogy class. We have so many clay minerals coming tonight. Bentonite, montmorillonite. When you're talking about clay minerals, you're simply talking about uh, the the mineralogy, right, of your clays. There, you also have physical clays, right? Physical clays do not necessarily contain clay minerals. Okay, physical clays could be simply um like silica or some lithic fragments, which are simply really just fine grained, like less than 4 microns. And physical clays or very fine soil grains can also have properties that are quite similar to your clay minerals. Okay. So again, physical clays can also will also have a large surface area per unit volume, and this would allow them also to trap water, and that would also allow them to have relatively low resistivities. Some ore minerals like graphite will also have very low resistivities. And for graphite, it's actually a not really straightforward way of considering graphite. Their resistivity will actually depend on the interconnectedness of the graphite grains, right? It's not about the concentration. Right? Let's talk about resistivity surveying. Right? One important principle is that resistance decreases with increasing diameter of the pathway of your current. Right? This actually sounds a bit counterintuitive because earlier we talked about increasing length, right? If you increase the length, you actually get more resistance. But this statement says that the resistance will actually decrease with increasing the diameter pathway. But yeah, actually this is not really contradictory. We also talked about earlier how increasing diameter or increasing the width of your pathway will actually decrease your resistance, right? So I think the way to illustrate this is that your current will essentially just spread out, right? For example, if this is your current, right? You're injecting some electrical current into the ground and it's flowing from this way to the other. Okay. As your pathway is starting to curve, right? As it's starting to curve, you're actually getting a bigger diameter, right? Your diameter is actually increasing. Okay. And this actually allows your current, this actually allows more electric particles to pass through this pathway. And I think it's similar to cars in a highway, right? Once you have a faster highway, you have more cars passing through, and some of the cars can actually just overshoot and overflow into a wider path, right? Okay. Anyway, I think the only point here is that once you inject current, right, as you try to increase the amount of current being injected, your pathway will simply spread out. Okay, okay, you will get a bigger and bigger radius, okay, of pathway. Okay. Right? And how do we do a resistivity survey? Basically, we are injecting current into the ground and we are trying to short circuit the ground basically. You're just trying to inject current okay from using two terminals. You have a positive and negative terminal. You just inject them into the ground and you just try to flow some current okay in between them. Okay, you're basically trying to turn the ground into an electrical wire. Okay, and just trying to let the current flow. Okay, and we use our convention here is to call the current. We call these points electrodes. They're essentially metal sticks, like metal stakes, which are connected to a battery as your power source. And electrodes or current electrodes are often abbreviated as C or it's like C1, C2, or A and B. Right? Right. And this is another important concept in surveying is that increasing electrode separation increases the depth of penetration. Okay. So again, if you inject your current from like if you're initially injecting current using this setup in B, like these are your two electrodes, okay? So they essentially are just passing their current okay through a relatively small pathway. Okay. However, as you try to increase their separation, right, you are now involving actually a bigger part of the ground, right? So you have now a bigger diameter for your pathway, or you have a thicker pathway now, or a wider pathway. And the result of that is that the current can actually now will tend to have a longer pathway. There, it's gonna try to compensate, right, for the lower resistance, and it will try to spread out. And the result is that you will have a bigger um, electrical pathway, and this will consequently uh, penetrate deeper into the subsurface. The general rule of thumb is that the separation length, right? If you multiply it by 30%, that's generally the penetration depth of your current. Okay. When I say penetration depth, that's the depth that is penetrated or reached by your current. Like, but in geophysics, penetration depth, that's essentially the depth which could be sensed by your geophysical method. Okay. The only consequence of increasing your separation and trying to have a larger penetration depth is that you're actually gonna get a coarser resolution or a less detailed survey as you try to go deeper. Again, same principle with the seismic surveys, if you will remember, right? And resistivity surveys, we are generally measuring the current, right? We are injecting current using a battery as our power source, and we we do know how much current we are trying to inject into the ground. So we know that I or current is actually a known quantity. We are also measuring the potential difference created by that's associated with that flow of current, right? And we do this by having another pair of metal stakes, or what we call electrodes. We have another pair of electrodes. We call it your potential electrodes. Where is that? Yeah, these are what we call the potential electrodes, and they're simply measuring the potential difference, right? They're just measuring the voltages on each of their points, and you're simply trying to measure the potential difference in between those 2 points. The typical voltages involved in resistivity surveys are between 100 to 300 volts, right? So it's not technically lethal, but at the same time, this is not really a comfortable amount of voltage to be exposed to. Current is commonly measured in, or current will usually be in the range of 1 ampere, while the potential difference is commonly read in units of millivolts. Right? I think at this point it would be important to go back again to our Ohm's law. So at this point, we already know that we know the voltage from our survey. We also know the current, and therefore we can now solve for our resistance. Okay. And yeah, that's basically how how resistivity works, right? From the voltage and the current, we can determine the resistivity. Oh, sorry, we can determine the resistance, although that's not yet our main parameter of interest, because resistance, again, is just a bulk property of the media. So again, we know now the resistance, and later on, we're gonna slightly discuss how we can determine the cross-sectional area of the current flow and the length. But generally, these things, the cross-sectional area and the length, they are simply related to the spacing of the current electrodes, right? So somehow we don't know exactly these things, but we can determine them from the electrode spacing. And therefore, from this point, we know the resistance. We can determine the cross-sectional area of the current flow and the length of the current flow. From there, we can solve for the resistivity of the material of the subsurface of the media. But again, the resistivity that we're actually measuring is just the apparent resistivity, right? So if you have multiple layers, which is almost always the case, you're simply measuring the average of so many layers, right? Okay, and again, just gonna discuss that in a bit. Let me go back to the discussion. Okay, so yeah, that's basically how the resistivity survey works. Okay, let me discuss a bit more few more points. Ions, right? This is one annoyance when we're doing a survey. Ions, again, as we've discussed earlier, these are actually moving. Ions, as long as there's a potential difference, ions can move, right? They will move to they're gonna be moving to the positive terminal, right? Because sorry, ions can be positive or negative, right? So the positive ions will go to the um negative current electrode, while the negative ions will go to the positive electrode. Either way, uh ions will concentrate on the electrodes, right? And they're gonna accumulate there. That's essentially the principle of electroplating, right? You're using electricity to cause your ions to attach to a surface, right? Like for example, a metal object, like you're just using electric current or electricity to attract ions to your metal object, and the result is that you will get a coating, like your electroplating, or your watch will have a gold plating, your ring will have a gold plating or whatsoever. Okay, and this a similar thing happens with ions when you're doing resistivity survey. They will accumulate on your electrodes, and that will definitely mess up with your potential difference readings, right? And the workaround here is the simplest way to work around this one, and this is actually the most commonly done way, is to simply to flip the current, right? A few times a second to disperse the ions. Okay. This is the most commonly done even in the most advanced resistivity methods. They simply flip the polarity of the current. Okay. Or they simply change the direction of the current. Okay. Or you can use metals which are less susceptible to polarization, like stainless steel or brass, right? In other methods, again, we're gonna segue a bit. In other methods like your spontaneous potential or induced polarization, they actually use a a ceramic pot, which actually is actually porous in a way that it's slightly leaking, and that ceramic pot will contain some solution containing ions, okay, of the metal that's being used. So, for example, if you have a copper electrode, you will have some copper sulfate solution. Okay. The purpose of the porous ceramic pot is that it's slowly leaking into the ground. It is causing it's causing grounding with the ground, right? So you're gonna it ensures that your electrodes are properly in contact with the ground, right? Again, at this point, our life is already complicated, and fortunately, we have another thing to deal with. Currents can also undergo refraction. Like what the F is this? To simplify how this works, right? Whenever you have a current, right, and it encounters a layer with a higher resistivity, the tendency of your current is to follow a steeper path, right? Okay. So yeah, just remember, higher resistivity, the steeper the dip, or the steeper the resulting dip of your current. On the other hand, if you're going from a higher resistivity to a lower resistivity boundary, the dip or the inclination of your current will become more gentle, right? Okay. And you can also see here, P1 is less than P2. So in here you are encountering a higher resistivity layer, right? And what happens here is that the dip or the inclination of the current will actually become deeper, and it will cause the current to penetrate deeper into the ground, right? So generally, actually, if your surface is so conductive, right, you will tend to have a generally slightly shallower penetration compared to a more resistive ground. Although this is not a straightforward matter, we also have another concern. It's what we call the contact resistance. If the electrodes are touching the ground or part of the ground which are too resistive, right? For example, a rubber is generally non-conductive. If you have inserted your electrodes, for example, on a layer of rubber tires, right? Your current won't even reach, will tend to be insulated, right? Within the contacts, and you won't be able to penetrate the subsurface. Okay? So contact resistance, or again, when you have shallow insulating layers like rubber tires, desert, very dry desert, dump a dump site that's full of plastic garbage. Okay. Um, or maybe a ground that's mostly just solid bedrock with minimal cracks and fissures, but that's very rare. Okay. Nevertheless, you can get contact resistance or almost zero penetration in these kinds of sites. Right? We've already talked about the concept of apparent resistivity. Now let's talk about the modes of doing resistivity surveys. Sounding is about measuring at a single point, right? So you're just trying to measure a single point of the ground or single location, single aerial location. Like you just have XY coordinate of the ground. And what we're trying to do with sounding is we're trying to measure the apparent resistivity of the shallow and then the deeper and deeper and deeper and deeper parts of the ground. Okay, so that we can sort of create a model or create a resistivity, a vertical profile containing different apparent resistivities per depth. Okay, so why do we do this? This is quite important if you're trying to locate aquifers, right? You're trying to locate conductive. Aquifers are generally conductive bodies, like they contain water. Okay? And again, resistivity generally is less expensive than drilling a borehole to look for water. But again, borehole drilling cannot be really replaced by geophysical methods. The only purpose of geophysics, again, is to simply extend, right? Extend the information that you have from boreholes. Like so if you have a borehole in this point and you have a borehole in this point and you want to know what's in between them, you can simply do so many resistivity surveys in between those 2 points, and from there you have a better understanding of a large area, right? With for the cheap for a cheaper price. Right? The depth of penetration of resistivity, again, I think this is a bit in contrary with the earlier discussion. But anyway, the depth of penetration of resistivity of rocks encountered are usually about 1/4 of the distance between the current electrodes. I think this is more conservative. Right? For example, if your current electrode spacing is 100 meters, the the depth that you're penetrating here would be 1/4 of that, or approximately 25 meters. For water exploration, right? If you're trying to explore for water or again aquifers, most of the drillings will try to reach anywhere between probably 100 to 200 meters. Okay? And if you're gonna try to do a resistivity that can penetrate that depth, you will need something like 400 meters to 800 meters of cable length, right? So it's a really, really large amount, or a lot of cable, like lots of electric cables needed to reach that target depth. Right? Profiling uses the same electrode distances for all the right. Sorry. Right. We discussed the sounding. That's one of the modes of resistivity survey. The other mode is profiling. Profiling is, instead of measuring the vertical, making a vertical profile, in profiling you're making now a lateral profile, right? Therefore, you are actually measuring the different points of the subsurface. Okay, you're measuring at different locations while the depth is gonna be the same. You're just trying to measure different locations using the same electrode spacing so that you can get the apparent resistivity at different locations of the ground. Again, this is another different application. This is useful if you're trying to locate something on a large area. Okay. Again, this could still be useful for aquifer or delineating the lateral extent of an aquifer, or maybe you're trying to delineate or locate a fault contact whatsoever, right? And although you can also combine, right? You can also combine profiling and sounding. So what you're gonna do here is you're gonna survey at different points using different spacings. So just move again to another point. Okay, I use different electrode spacing so that you can penetrate deep into the ground. And the result is that you're gonna get so many apparent resistivity readings at different depths. Okay, and from there you can create a 2D profile of apparent resistivities. Okay, so again, this is just apparent resistivity, right? You're still not really measuring the actual resistivity of the layers in the subsurface. You're simply measuring the average, okay, of your layers at different depths. Okay, so this is just a graphic on how showing how a 2D profile works. Okay. Right, and we're also gonna talk about different electrode configurations. Right, originally the resistivity method was made for finding conductive bodies, and high resistivity anomalies, yeah, can still be detected using different electrode arrays. As long as you have a dense layout, meaning you have a closely spaced survey. And resistivity, as we have discussed earlier, will consist of your current electrodes, your C1 and C2, and also your potential electrodes, your P1 and P2. Okay, so you essentially have four electrodes. Although there are many ways in which you can arrange your current electrodes and your potential electrodes. Okay, so the most simple array or arrangement is that you're simply passing your current through the outside, and then you have your potential electrodes measuring on the inside. Okay, and of course, this is the simplest one. There are many other arrangements or arrays in which you can do resistivity survey. Um, yeah, and these are the most common arrays. Your Venner, German, W becomes V. Yeah, Venner array, Schlumberger. This one is French, so the Ger becomes J. Pole, dipole, and then dipole, dipole. Right? So these are the most common arrays. I'm gonna go back to that later. Okay. Right, let's first talk about the correction factors for the geometry. So again, earlier I talked about yeah, right. Again, I said that we know the voltage during resistivity survey. We also know the current, so therefore we can determine the resistance of the bulk resistance of the subsurface. And from the resistance, we can actually determine the resistivity as long as we know the geometry of the flow path of the current. But we actually don't really directly calculate, we actually don't really directly know the diameter and length of the pathway. Instead, we use a geometric correction factor, right? So in order to calculate the resistivity, we simply multiply the resistance. So this V divided by R we can simplify that to your resistance. So resistivity is simply equal to your resistance multiplied by your array constant. Or this is simply the geometry constant of your array. Okay? So this constant is simply like a proxy for the diameter and the length of your electric current flow path. And K, or the constant of the array, will differ for every survey that you do. So it will depend essentially on the spacing between your individual electrodes, right? And here you can see that K is equal to 2 pi divided by the quantity of 1 divided by the spacing between your current electrode 1 and potential electrode 1 minus the value of 1 divided by this the distance between electrode 1 and potential electrode 2, and so on and so forth. Okay? So I don't need to memorize that. Just the only thing you need to remember is that your resistance is related to your resistivity by your array constant. And this is actually not really a constant because it always differs. Uh, it's really more of a correction factor, right? It's really a geometric correction factor, which will depend on the distances between your electrodes. Okay. So we're gonna discuss the different arrays. The array type will also influence this one. The electrode spacing, of course, will also influence this one. So for example, if you're trying to measure deeper and deeper, of course, you will have different distances between your different electrodes, and your K correction factor will change. Okay. Okay. Right, just a few more points. If the potential is too small to be accurately read, you might need a better electrode grounding. Like as I mentioned earlier, you might need to either have maybe a bigger electrode contact, or maybe add some solution, pour some water into the ground, or pour some solution into the ground, or have a bigger battery as the source of your current, right? Or increase the distance between your potential electrodes so that you have a bigger potential difference. Okay. Right. So I mentioned the Schlumberger, the Venner, the pole dipole. So these are the common arrays, and these arrays are actually part of different array groups. The first one is your potential array. Potential arrays just measure the potential between two distant electrodes. The consequence of that is you get to measure a large potential difference. So again, my analogy here is your potential energy. Like the higher you are from the building, the higher the potential energy. That applies again to resistivity, right? The bigger the spacing, the bigger the potential difference. So the bigger the spacing of your potential electrodes, the bigger the potential difference you're gonna measure. And this is good for survey sites where you have a lot of noise. Okay? Because when you have a big potential difference or you're reading big voltages, you can actually sort of overcome the electrical noise. Okay. This is also useful for areas with poor grounding, right? So again, when you have this kind of array, you are dealing with large potential differences, and consequently, you will also need a bigger current. Okay, so you'll be using a more powerful energy source here. And yeah, you can this is useful for overcoming noise and also surveying in an area with poor grounding. Right? And an example of a potential array is the Venner array, right? This is the setup of your Venner array. It's a potential array. It's the simplest looking geometry. You simply have your current being injected on the outside, and then you have your potential electrodes on the inside, and their distances are always equal. Okay, A is equal to A is equal to A. So this is very simple. The other one is your the other group of array is the gradient array. And in here, you're measuring the potential difference between two closely spaced electrodes. And the example of this one is the Schlumberger array. What we're trying to do here in the gradient array is we're trying to close down or have a very, very small distance between between the two potential electrodes. Like it's almost zero distance in practice. Okay. So the theory here is that if you have a two closely spaced potential electrodes, you can actually measure the first derivative of the potential or the gradient of the potentials. So I'm gonna show the setup of a Schlumberger array. One thing you'll note here is that the potential electrodes are actually very closely spaced, right? Sometimes they use a zero spacing or almost an almost zero spacing, while the current electrodes are going to be quite far apart. Okay, relatively speaking. The advantage the advantage of Schlumberger array is that you are measuring changes in resistivities, like you're measuring the gradients, and therefore this is going to be very sensitive to boundaries. Okay, so if you're trying to delineate or locate the contact between two boundaries, Schlumberger is quite good. Okay, the downside of gradient arrays or for example Schlumberger array is that the since the potential electrodes are so closely spaced, right? You are now just measuring a very low potential difference. And any sort of noise can easily influence this kind of reading, right? So if you have maybe something like a buried electrical line, this can greatly influence or basically mess up your readings. Okay, so it's sort of an opposite to the Venner array. The Venner array is good for areas with a lot of noise, but this one is actually quite bad at locating boundaries. Okay, because the potential electrodes are quite spaced apart. Schlumberger array, on the other hand, is you have two potential electrodes that are closely spaced, and they simply measure the changes in the resistivity. So they're actually good at spotting boundaries of your subsurface objects. The third group are the dipole arrays. They're actually the most sensitive. And the downside of that is that they're really highly affected by noise. Right? And you have two common arrays under the dipole array. You have the pole dipole and dipole dipole array. In the pole dipole array, the one of the electrodes is further from the measuring dipole than the second one. So let's look at. Okay, so in this one, you have a dipole, meaning you have a pair of a current and potential electrode. And then you have, sorry, right? So in here, you have your current electrode on the outside, and then you have your potential electrode on the inside. And the potential pair is closer to one end of to one end of your current electrode, and this other current electrode is infinitely far away, okay, from this one. So this is very, very, very far. Okay, so this electrode is very far away from the other electrodes. Okay, that's quite lonely. On Okay, so again, so in here again, the second current electrode is very far away, and this is at least 5 times the distance between the current electrode and the measuring potential dipole. So current electrode and the measuring potential dipole. So this distance is gonna be like 5 times of this distance, right? So what they actually do in a pole dipole array is they usually do this. So they measure in this point and they also measure in this point. Okay, and they sort of get a pair of values. Okay, and this is very useful for profiling or for mapping the lateral changes and resistivities. Okay, yeah, I think mainly because you have a good ratio between between your sensitivity and noise. Okay, so we discussed already the Venner and the Schlumberger array. Now for the other one, the dipole-dipole array, this is the most sensitive to noise, right? As you can see here, the setup is that you have a pair of current electrodes on one end and the pair of potential electrodes on the other end, right? So the depth estimate for this configuration is about one-fourth the distance between the centers of the dipoles. So this one, right? The penetration depth here is one-fourth of this distance between these two dipoles. So the advantage of dipole-dipole array is that you can actually get a very long, you can get a very deep penetration for less amount of array length, right? So you need a shorter array, okay, with a dipole-dipole array to get a very deep reading compared to the other resistivity arrays. Okay. However, again, this is quite sensitive to noise because as you can see here, the two potential electrodes are so closely spaced together. So you're simply measuring very small potential differences. And again, whenever you're measuring you are dealing with small values, you're very much susceptible to noise, right? Okay, so you can see here the different patterns created by different arrays, right? So if you have here a highly resistive body in the middle and low resistivity bodies on the others and either sides, the most simple image the Venner array will simply have the simplest image here. The Schlumberger array will be good again at delineating the boundaries. So you can see here, this is the boundary, right? This is the boundary of the middle body, right? And it's really sharply delineated in the Schlumberger array. And then the most weird or like the most complex image is gonna be the dipole-dipole array. Okay. So you can see here, the dashed line is the reverse array and the solid line is the forward array. So they usually just superimpose it so that they can determine the midpoint of the conductive of the anomalous object. Okay. Okay, so I've already discussed that. Let's talk about vertical electrical sounding. Right, vertical electrical sounding is, again, this is simply sounding. You're simply measuring at a single location and then you're just trying to have an increasing potential electrode separation. Okay, so that you can penetrate deeper and deeper. And it's usually useful for hydrogeological applications like locating aquifers or finding the depth of your bedrock. And the most commonly used array for vertical electrical sounding is the Schlumberger array, because Schlumberger array only needs you to move the current array. Okay, so let's go back again to the Schlumberger array. So again, so in here in the Schlumberger array, you have here the potential electrodes measuring the potential difference. So what you're gonna do here is you're gonna measure, right? You're gonna measure one reading here, and then the next reading you will need to simply move away the current electrode so that you can penetrate deeper. And then you just move and move the current electrode so that you can penetrate deeper and deeper and deeper until you can get a vertical profile of the subsurface. Right? And the results are usually plotted on a log-log graph, mainly because a logarithmic plot tends to diminish, right? It tends to diminish, increasing large values. And we use a log-log plot for this survey because as you get deeper and deeper, you are getting coarser and coarser resolution. So there's really no sense to have a constant spacing as you go deeper, right? Because you're simply having a very granular resolution as you go deeper. Therefore, the practice is to simply try to increase exponentially the electrode spacing as you go deeper and deeper, because you simply have a coarse resolution at depth anyway. Okay, so they simply plot this x-axis is the apparent resistivity. Okay, so again, apparent resistivity is the average resistivities of all the layers being penetrated. And then the y-axis is the AB divided by 2. This is simply the spacing of the current electrode divided by 2. Okay, so don't have students anymore. Talk about inversion. Inversion is the process of it's a process for obtaining more or less the resistivities of the layers from an apparent resistivity. Okay, one of the concepts of inversion is that there's usually no unique solution, right? For example, when you have a thin layer, right? So when you have a thin layer, um, a thin layer can be reproduced by a layer of different thinness, as long as their product, their thickness and their resistivity is gonna be the same. Okay. So you can have a thick layer with a low resistivity or a thin layer with a high resistivity. It doesn't matter, as long as they have the same product, their response will be the same. And therefore there's really no unique solutions for these layers in the inversion process. Okay. In the olden times, they used the master curves for inversion. Okay. And they simply match the plot of the resistivity with these master curves. So, and from this one, you can determine different indices. The depth index will give you the depth of the boundary between two layers. The resistivity index will give you the ratio of resistivity between the two layers, and then the K value will give you the thickness of the two layers, right? If your subsurface has three or more layers, you will simply be splitting the model into multiple two-layer cases, right? But for our purposes, we're gonna be doing this mostly in the computer, and we're gonna be simply doing a less rigorous way of inversion in the exercise. Okay, I think this only important stuff here is that the black line here is the measured resistivity. This is the measured apparent resistivity, while the blue line is the model resistivity. And this is the resistivity per layer, okay, of our, but this is still a model, right? So it's just this is just our interpretation of the resistivity values of the layers. And we can verify if this is mathematically correct by generating another set of apparent resistivity from the model and comparing it with the measured apparent resistivity. If the two apparent resistivities are matching, we can say that the model is mathematically accurate, okay, but not necessarily geologically accurate. Okay, so I think I'm gonna stop here and just continue the discussion in the exercise probably on the next session.